All right, let's jump right in. Today, we're going to tackle a question that's, well, fundamental to how computers work. How do they handle priority? I mean, when you've got a million things to do, how do you always know what to do next? It's a puzzle our tech solves every single second. And today, we're going to find out exactly how.
I mean, really think about it for a second. Your computer's CPU, it's juggling hundreds, maybe thousands of tasks at once. Your GPS is figuring out the fastest route, like right now. And what about a hospital ER? They have to decide who gets treated first, and it's a life or death decision. So how do they all instantly know what's the most important thing to do? Well, it's not magic, not at all. It's an incredibly clever data structure.
And this isn't some abstract theoretical problem, right? We're talking about real-world stuff. CPU task scheduling, where that one critical process has to get the resources first. Or the logic behind that triage system we just mentioned. It's even at the very core of famous algorithms like Dijkstra's, the one that finds the shortest path on a map. All of these things, they absolutely need a system that can just hand over the highest priority item instantly. So what's the secret sauce? What is this specialized tool? Well, it's time to meet the binary heap. And trust me, it's an elegant and super efficient data structure that was built for one job and one job only, keeping track of what's most important. Okay, so what in the world is a heap? At its heart, it's a special kind of binary tree. It's what we call a complete one, and it follows one really simple rule. If it's a max heap, every parent node is bigger or equal to its kids. That means the absolute biggest item is always sitting right there at the top. And for a min heap, you guessed it, it's the exact opposite. The smallest item is always at the top. Pretty straightforward, right? Now, it's super easy to get a heap mixed up with a binary search tree, a BST. But listen, their jobs are completely different. A BST is all about being fully sorted, which makes it awesome for searching for stuff. A heap could not care less about that. It's obsessed with just one thing, keeping that top priority item right at the root for instant. We're talking O of 1 access. Trying to search a heap is a mess. So the bottom line is simple. Use a heap for priority, use a BST when you need to find things fast. Okay, so how does it pull this off? How does a heap keep this perfect priority system running so smoothly and efficiently? Well, it all boils down to two really simple but super powerful rules that it has to follow, no exceptions. Yeah, these are the two golden rules. Rule number one is the structural property. It must be a complete binary tree. All that means is that it's filled up from left to right, level by level. No gaps. Think of it like filling seats in a movie theater. You fill the first row, then the second, no skipping seats. Rule number two is that heap order property we just talked about. Every single node has to play by the rules. Either max heap, where dad's bigger than the kids, or min heap, where dad's smaller. These two rules, working together, are the whole secret to its power. And now for the big twist, the aha moment. You see this thing that looks like a tree with all its nodes and branches, but we almost never build it that way with complicated pointers. So how do we do it? We use a plain, simple array. That's it. And this is what makes it so incredibly fast and memory efficient. But wait, how do you navigate a tree structure when it's just a flat array? Well, this is the really cool part. It's just simple math. For any element at some index I, you can instantly find its parent and its kids using these formulas. It's insanely fast. There's no chasing pointers all over your computer's memory. It's just a little bit of arithmetic. That's the magic right there. That's what makes this array trick so powerful. Okay, so what happens when we need to add a new item to our priority list? The process is called heapify up, or sometimes bubble up. First, you just stick the new element at the very end of the array. Easy. That keeps our complete tree structure happy. But it might break our heap order rule. So to fix it, we compare the new kid with its parent. If it's out of order, we swap them. And we just keep doing that, letting it bubble up the tree until it finds its rightful place and everything's back in order. And what about taking out the most important item, the one at the top? That process is called heapify down, or sift down. Here's the trick. We take the very last element in our array and put it at the root. Then we shrink the array, getting rid of that last spot. Now, our tree structure is still complete, but our heap order is probably a total mess at the top. So we take that new root and sink it down. We compare it with its children, swap it with the bigger one in a max heap, and keep doing that until it settles into the right spot and the heap is a happy family again. All right, so we've seen the mechanics, the nuts and bolts. Now for the payoff. Where do you actually find this thing out in the wild? Where is it being used?
Honestly, once you know what to look for, you'll see heaps everywhere. They're the engine inside every single priority queue. They're absolutely essential for those famous graph algorithms like Dijkstra's for finding the shortest path and Prim's for finding minimum spanning trees. They're the whole basis for a really slick sorting algorithm called Heapsort. And they're amazing for problems like, hey, find the top 10 highest scores out of a list of 1 million people without having to sort the whole dang list.
And yeah, speaking of sorting, Heapsort is a total classic. The idea is brilliant. You just build a max heap out of your data, and then you just keep plucking off the biggest element one by one. Bam, your array is sorted. The efficiency is O(n) log n, which is just a fancy way of saying it's really, really good. It scales incredibly well as you throw more and more data at it. It's right up there with other speed demons like merge sort, but it has one huge advantage. It sorts in place, meaning it doesn't need a bunch of extra memory to do its job.
Okay, so the theory is awesome, but let's get practical. What if you need to use one of these in your own code? Say in C++. Do you have to build this whole thing from the ground up? Thankfully, the answer is a big, fat no.
The C++ standard template library, the STL, has got your back. Forget about manually managing arrays and writing your own heapify functions. You just use a container that's already built for you, std priority queue. And guess what? Under the hood, it's just a heap. You get all the awesome performance benefits with absolutely none of the headaches of building it yourself.
And just look at this, it's this simple. That one line of code, that's it. That gives you a fully functional max heap ready to hold integers. You can push new items in, and whenever you ask for the top one, boom, it'll give you the biggest value in the queue. It's powerful, it's been tested to death, and it's just sitting there waiting for you to use it.
All right, let's start to wrap this up. We're going to go over the most important things you need to remember, and maybe even more importantly, the common traps people fall into when they first start using heaps. So here's your heap cheat sheet. What do you need to know? 1. A heap is a complete binary tree, but it's almost always stored as a simple array. It's a clever trick for speed. 2. Its only goal in life is to give you instant access to the max or min element. 3. Adding and removing stuff is super efficient, O of log n. And 4. If you're in C++, your new best friend is std priority queue. Just use it. And finally, let's talk about the rookie mistakes to avoid. First, and this is a big one, don't ever think a heap is fully sorted. It is not. Only the top element is guaranteed to be in the right place. That means you should never, ever use a heap when you need to search for something. That's a job for a binary search tree or a hash map. And hey, if you're brave enough to build one from scratch, triple check your index math and never, ever forget that complete binary tree rule. So there you have it, the binary heap, totally demystified. It's a simple, elegant, and seriously powerful tool that lets computers figure out what's most important in the blink of an eye. The only question left is, now that you understand this tool, what complex, messy priority problem are you going to go out and solve first?